welcome back to Deep Space Dreams, where we drift through the deep past, one story at a time. Tonight we're going on a slow, soothing journey into one of the most gentle and profound cosmic mysteries of recent times. A mystery born not from a loud explosion or a dramatic collision, but from a quiet fading, a silent disappearance. We're journeying toward a traveller from the cold, dark edge of our solar system, a visitor that promised a spectacular show, only to vanish like a ghost. Tonight we ask, did we misread Comet 3I/ATLAS from the very beginning? As always, I hope this video helps you drift off gently, or at least helps you put your worries into perspective by zooming out a few 100,000 years. Of course, there's a small risk that it might be too interesting and keep you awake. But if that happens, well, at least you'll have learned something fascinating along the way. Before we float off into the past together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow. I'd also love to know where you're watching from and what time it is for you right now. Let me know in the comments. It's always such a joy to see our sleepy history community scattered gently across the globe, all settling in under different stars. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like whispers on the wind. And as we begin this gentle voyage into the vast unknown, remember this video is for educational and relaxation purposes only and is not intended as medical advice. Ready? Let's begin. Our story begins not with a flash, but with a quiet hum. The sound of electricity flowing through circuits, of cooling fans spinning in the deep of night. It begins in the silent, tireless work of machines that have been given a profound purpose: to watch, to stare, unblinking into the cosmic dark night after night, year after year. These are the robotic eyes of our planet, telescopes scattered across the globe, from the high, dry deserts of Chile to the volcanic peaks of Hawaii. One such system, a pair of telescopes, is called ATLAS, the Asteroid Terrestrial Impact Last Alert System. Its name sounds urgent, designed to find objects that might pose a threat. But most of what it finds is not a threat at all. Most of what it finds is simply there, ancient, silent, and moving. Imagine you are one of these telescopes. Your world is the night sky. The moon waxes and wanes, a familiar rhythm. The great cloudy river of the Milky Way turns slowly overhead, a constant companion. And against this backdrop, countless tiny points of light. The stars, so distant they appear fixed, unmoving, a permanent map of the heavens. But your job is to notice what isn't permanent. Your electronic mind is built to compare tonight's sky with last night's and the night before that. You're looking for the wanderers, the little smudges of light that have shifted their position against the stellar map. Most of these are familiar neighbours, asteroids, drifting in their ancient belt between Mars and Jupiter, known comets, returning on their predictable paths. But every so often, you see something new. On a quiet night in the last days of 2019, the ATLAS telescope on Mauna Loa, Hawaii, did its job perfectly. It took a picture of a patch of sky, then another, and in its digital mind, it compared them, and there it was, a faint, fuzzy spot of light that wasn't there before. It was incredibly dim, thousands of times fainter than the faintest star you could ever hope to see with your naked eye. It was just a handful of pixels, a ghostly stain on the darkness. To anyone else, it would be nothing, a speck of dust on a lens, a glitch in the sensor. But the system knew better. It checked again. The smudge was still there, and it had moved just a tiny amount, consistent with an object very, very far away, falling in towards the sun. An alert was sent out. Not a loud alarm, but a quiet digital message sent across the internet to a clearinghouse for astronomical discoveries. A new object had been found. It was given a temporary name, a string of numbers and letters, and astronomers around the world in their own quiet offices and observatories began to take notice. They pointed their own telescopes, bigger and more powerful, toward those same coordinates, and they confirmed it. It was real. A new comet had been discovered. It was officially designated C 2019Y 4A-TLAS, named for the survey that found it. The C told us it was a long-period comet, a visitor on a journey that takes more than 200 years, likely thousands. The 2019 Y4 was its license plate, a marker of when it was found. There was nothing at first to suggest this comet was special. It was just one of a dozen or so discovered every year, a faint, distant traveller from the Oort cloud. Imagine this place, the Oort cloud. It isn't a cloud in the way we think of them on Earth. It is a vast spherical shell of icy bodies surrounding our entire solar system. It is the deep freeze, the cosmic attic where the leftover building materials from the formation of the sun and planets have been stored for 4.5 billion years. It is so far away that the sun is just the brightest star in the sky. The distances are almost impossible to comprehend. If our solar system out to Neptune were the size of a coffee cup, the Oort cloud would be a sphere enveloping the entire city it sits in. Out here, trillions of icy bodies drift in a slow cosmic ballet. They are perfectly preserved relics of the primordial nebula from which we were all born. For billions of years they float in the absolute cold and dark, undisturbed. But sometimes something happens. The gravitational nudge of a passing star, a subtle tide from the galaxy itself, and one of these icy bodies is dislodged from its stable orbit. It begins a long, slow fall, a journey that can take millions of years, falling, falling, falling toward that one bright star in its sky, the sun. This is the journey that Comet ATLAS was on. For eons it had been a quiet resident of the outer darkness, and now it was making its very first trip into the inner solar system. It was a true primordial object, an untouched piece of history, now coming into the light. And as it fell, as it crossed the orbit of Jupiter, then Mars, something remarkable began to happen. It started to get bright. Much, much brighter than a normal comet would from that distance. The faint whisper was starting to raise its voice. Astronomers measure the brightness of objects in the sky using a scale called magnitude. The lower the number, the brighter the object. When it was discovered, Comet ATLAS was a dim magnitude 19. As it moved through the first months of 2020, its brightness began to soar. 17, 15, 12. It was brightening at an almost unprecedented rate. Projections were made. Calculations were run on computers, extrapolating this trend forward, and the results were astonishing. If it kept this up, by the time it made its closest approach to the sun in May, it could reach magnitude 1 or even 0. That's as bright as the brightest stars in the sky. It could even become a great comet. A great comet is not an official designation. It's a title of honor bestowed by humanity on those rare comets that become so bright they are easily visible to the naked eye, often sporting a long, dramatic tail that stretches across a huge portion of the night sky. They are cosmic events that capture the imagination of the entire world. Think of Hale-Bopp in 1997, hanging in the sky for months, a silent, majestic presence. Or Halley's Comet returning every 76 years, a reliable celestial friend woven into the fabric of our history. These events are rare. They connect us to the sky, to the scale of the universe, in a visceral way. They remind us that our world is part of a much larger dynamic system. And Comet ATLAS seemed poised to become the next one. The promise was intoxicating. In a world that felt increasingly complex and troubled, here was a gift from the cosmos. A simple, beautiful spectacle for everyone on Earth to share. Stargazing communities were buzzing. Articles were written. People who had never looked through a telescope were learning the name ATLAS. They were looking up at the sky, trying to find this new visitor. In those early months, it was still too faint for most, a prize for amateur astronomers with good equipment and dark skies. They shared their photos online, a fuzzy greenish ball, the coma, the atmosphere of gas and dust boiling off the comet's icy heart, its nucleus. The nucleus itself is tiny, usually only a few kilometers across, a city-sized block of ice and rock. But as the sun's radiation hits it, the ice doesn't melt, it sublimates, turning directly from solid to gas. This gas expands outwards, carrying dust with it, creating a temporary atmosphere that can be larger than a planet. This is what we see, and the green glow of ATLAS was particularly beautiful. It comes from diatomic carbon, molecules of two carbon atoms bonded together, which are broken apart by sunlight and then glow in a specific ethereal green wavelength. It was the colour of a cosmic ghost. The whisper in the dark had become a song of promise, a promise of wonder, a promise of a shared experience. We, on our small blue planet, were about to receive a guest from the dawn of time, a guest that had travelled for millions of years just to put on a show for us. We were watching it, tracking it, celebrating its arrival. We were projecting our hopes onto it. We saw its rapid brightening not as a sign of anything unusual, but as a sign of its strength, its vitality. We saw a robust and powerful object ready to dazzle us. But the universe is not here to meet our expectations. It operates on its own terms, by its own ancient laws. And the story of Comet ATLAS was about to take a turn that no one predicted, a turn that would transform it from a story of spectacle into a story of profound and gentle mystery. We thought we were reading the opening chapter of a grand, triumphant epic, but perhaps we were misreading it from the very beginning. Perhaps the comet's brilliant flare was not a sign of strength but a cry, the final, brilliant flash of a fragile body being torn apart by forces it had never before encountered. The faint whisper from the dark was not a greeting, it was a goodbye, and we, in our excitement, had simply misunderstood. We were listening for a song, but what we were hearing was the sound of an ancient thing, quietly, gracefully unravelling. And in that unravelling, a deeper, more contemplative beauty was waiting to be found. A beauty not of spectacle, but of silence. The beauty of a fleeting moment, a ghost in the machine of the solar system, reminding us that some of the most profound stories are the ones that end not with a bang, but with a quiet, fading whisper. Consider the nature of discovery itself. When we find something new in the cosmos, we bring to it all our human baggage, our hopes, our fears, our desires for meaning and pattern. The ATLAS survey system, that patient electronic watcher, had no such expectations. It simply recorded what it saw, a moving point of light. But the moment that data reached human minds, it became something more. It became a story. And stories, we know, are shaped as much by the listener as by the teller. In those early weeks of 2020, as the world was beginning to grapple with challenges none of us had anticipated, the comet became a kind of cosmic comfort. Here was something pure, something untouched by earthly concerns, a reminder that the universe continues its ancient dance regardless of our small dramas. People began to plan viewing, parties for May, telescope sales increased, children learned about comets in hastily assembled homeschool lessons. The comet was becoming woven into our collective consciousness, a bright spot in an increasingly uncertain time. But even as we celebrated, even as we anticipated, the comet was already changing. Deep within its icy heart, forces were at work that we couldn't see. The same solar radiation that was causing it to brighten was also causing stress fractures to spread through its ancient ice. Imagine a snowball that has been kept in a freezer for billions of years, suddenly exposed to a blowtorch. The surface begins to sublime violently, jets of gas erupting from weak points. The spinning of the nucleus, once stable, becomes chaotic as these jets act like tiny rockets, pushing and pulling in different directions. This is normal for comets. They all experience these forces, but most comets have made this journey before, perhaps many times. They have been tempered by their passages near the Sun, their volatile ices already depleted, their structure consolidated. They are veterans of the inner solar system, but Atlas was different. This was its first time. It was what astronomers call a dynamically new comet, fresh from the Oort cloud, never before exposed to the Sun's intense radiation. And that freshness, that pristine nature that made it so scientifically valuable, also made it vulnerable. The brightness we were seeing, that exponential increase that had us all so excited, was perhaps not a sign of a spectacular show to come, but rather the comet literally coming apart at the seams. Each burst of brightness was another chunk of the nucleus exposing fresh ice to sunlight, another fracture propagating through its structure. We were watching not a crescendo, but a dissolution. And yet, how could we have known? Our experience with comets told us that brightness meant size, meant robustness. We had no reason to suspect otherwise. The story of human understanding of comets is itself a long journey from fear to fascination. For most of human history, comets were omens, harbingers of doom or change. The word disaster literally means bad star. Ancient Chinese astronomers called them broom stars, sweeping away the old order. Medieval Europeans saw them as warnings from God. It wasn't until Edmund Halley, in the early 18th century, proved that comets were celestial objects on predictable orbits that we began to see them as natural phenomena rather than supernatural messages. And yet, even with our modern understanding, even with our sophisticated models and powerful telescopes, comets still surprise us. They are in many ways the most unpredictable objects in our solar system. Each one is unique, a product of its particular history and composition. Some, like Halley's Comet, are reliable as clockwork. Others, like Atlas, remind us that the cosmos still holds mysteries, still has the capacity to confound our expectations. As February turned to March in 2020, amateur astronomers around the world were tracking ATLAS nightly. They were sharing their observations on forums and social media, comparing notes, updating their predictions. The comet had become bright enough to see through binoculars from dark sites. Its coma had expanded to an enormous size, wider than Jupiter. The excitement was palpable. This was it. This was going to be the comet of a generation. But then, subtle changes began to appear. The coma, that beautiful green cloud, seemed less uniform. Instead of a smooth circular glow, observers began to notice irregularities, elongations, asymmetries. At first, these were dismissed as effects of solar wind or viewing angle, but as days passed, the changes became more pronounced. Professional astronomers began to take notice. Something was happening to Comet ATLAS, and it wasn't what anyone had hoped. The first definitive evidence came from the Hubble Space Telescope in early April. Hubble, floating above Earth's atmosphere, has an unparalleled view of the cosmos. When it turned its eye toward Atlas, what it saw was both heartbreaking and fascinating. The nucleus of the comet wasn't a single object anymore. It had fragmented. Where once there had been one icy body, there were now several, maybe dozens, of smaller pieces, each surrounded by its own small coma, drifting slowly apart. The realization spread through the astronomical community like a wave. The great comet we had all been anticipating was no more. It had disintegrated before our eyes. The brightness we'd celebrated had been its death throes. We had been watching a 4-billion-year-old piece of our solar system's history destroy itself, and we had mistaken it for a greeting. The disappointment was real and widespread. Media outlets that had been hyping the comet of the century now had to explain its demise. Amateur astronomers who had invested in new equipment felt a sense of loss. Children who had been learning about comets, drawing pictures of Atlas with its magnificent tail, had to be told that the show was cancelled. The universe, it seemed, had played a cruel joke on us. But perhaps that's the wrong way to look at it. Perhaps the universe hadn't promised us anything at all. We had made the promise to ourselves based on our interpretation of the data, our extrapolation of trends, our deep human need for wonder and spectacle. The comet had simply done what it was always going to do, followed the laws of physics that govern all matter. It had come from the cold and dark, ventured too close to the sun and paid the price. And in that destruction, in that gentle dissolution, there was still beauty, still wonder, just not the kind we had expected. The Hubble images of the fragmented nucleus were hauntingly beautiful, like a string of pearls scattered across black velvet, each fragment glowing with its own light, each following its own slightly different path. We were witnessing something rare and precious, the death of a primordial object, the transformation of something ancient into something new. Think about what those fragments represent. Each one is a piece of the original solar nebula, the cloud of gas and dust from which our sun and all the planets formed. For 4.5 billion years, that material had been locked in the deep freeze of the Oort cloud, unchanged, unaltered. And now, in the span of a few weeks, it was being dispersed into the inner solar system. Some of it would fall into the sun, some would be blown out by solar wind, and some perhaps would find its way to Earth, adding its ancient atoms to our world's inventory. We are, all of us, made of stardust. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of it was forged in the hearts of dying stars billions of years ago. And comets are the delivery system, the cosmic postal service that has been bringing these elements to Earth since its formation. Every comet that disintegrates in the inner solar system is seeding space with organic molecules, water and other compounds essential for life as we know it. So perhaps Atlas did give us a gift after all. Not the gift we expected, not the spectacular light show we had hoped for, but something more subtle, more profound. It gave us a front row seat to a process that has been happening since the dawn of the solar system. It reminded us that creation and destruction are two sides of the same coin, that endings can be as beautiful as beginnings, that sometimes the most meaningful moments are the quiet ones. The story of Atlas also highlights something important about the nature of scientific observation in our modern age. Never before have we had so many eyes on the sky. Professional telescopes, amateur astronomers, automated surveys, space-based observatories. We're watching the heavens with an intensity and consistency unprecedented in human history. And because of this, we're catching events that would have gone unnoticed in previous generations. We're seeing the universe not as a static backdrop, but as a dynamic, ever-changing theatre. This comprehensive coverage allowed us to follow Atlas from its discovery to its dissolution in exquisite detail. We have thousands of images, countless spectra, measurements of its composition, its rotation, its trajectory. Even in its destruction, Atlas has become one of the best-studied comets in history. Every fragment, every puff of gas, every grain of dust has been catalogued and analysed. In death, it has given us more scientific data than many comets provide in their entire visible lifetime. Consider what we learned from those observations. The rapid brightening that had us all so excited was caused by an unusually high proportion of highly volatile ices, not just water ice, but frozen carbon monoxide, methane, and other compounds that sublimate at much lower temperatures. This told us that Atlas had indeed never been close to the Sun before. It was a true pristine sample from the Oort cloud, unaltered by previous passages through the inner solar system. The fragmentation pattern told us about the comet's internal structure. It wasn't a solid block of ice, but rather a loosely bound collection of smaller pieces held together by weak forces. Astronomers call this a rubble pile structure. Imagine a snowball made not by packing snow tightly, but by gently pressing together a handful of smaller snowballs. The slightest stress could cause it to fall apart. And that's exactly what happened when Atlas encountered the sun's heat. The colour of the fragments changed as they separated, telling us about compositional differences within the original nucleus. Some pieces were bluer, indicating more water ice. Others were redder, suggesting a higher concentration of organic compounds. It was like watching a 4-billion-year-old time capsule break open, revealing the varied ingredients from which our solar system was made. The speed at which the fragments separated told us about the forces involved in the breakup. It wasn't a violent explosion, but a gentle drifting apart, like dancers slowly leaving a stage. This suggested that the breakup was caused not by a sudden event, but by a gradual accumulation of stress. The comet had been dying for weeks, maybe months before we noticed. We had been watching a slow-motion catastrophe, beautiful in its inevitability. And what about those fragments now? Where did they go? Some continued on their journey around the sun, each now a small comet in its own right, too faint for most telescopes to follow. They will continue to orbit, gradually losing more mass with each passage until they are nothing but streams of dust and gas. Others may have been pushed by solar radiation pressure into new orbits, perhaps to return in hundreds or thousands of years, perhaps to be ejected from the solar system entirely. The dust released by Atlas's disintegration has spread out along its orbital path, creating a new meteor stream. In the future, perhaps decades or centuries from now, Earth might pass through this stream. When it does, we might see meteors, shooting stars that are literally pieces of ATLAS burning up in our atmosphere. Children not yet born might make wishes on falling stars that are fragments of the comet we watched die in 2020. This is the true nature of comets. They are not permanent fixtures of the night sky, but temporary phenomena, transitional objects caught between being and non-being. Every comet is in the process of destroying itself. Some do it quickly, like Atlas. Others, like Halley's comet, do it slowly over thousands of orbits. But all of them are ephemeral, and that ephemeral nature is part of their beauty. Think about how this mirrors our own existence. We too are temporary arrangements of matter and energy, briefly organized into these patterns we call ourselves. We too are in constant flux, our atoms cycling through us, our cells dying and being replaced. We too will eventually disperse, our elements returning to the Earth and perhaps eventually to the stars. In watching Atlas, we were watching a cosmic reflection of our own mortality, played out on a scale and timeline that dwarfs our human experience. But there's something else to consider about Atlas, something that brings us to the heart of our question. Did we misread it from the beginning? The answer might be more complex than a simple yes or no. Perhaps we read it exactly as we were meant to, as we needed to. Perhaps the misreading was part of the story, part of the gift. Human beings are meaning-making creatures. We see patterns in clouds, faces in rocks, stories in the stars. This is not a bug in our cognitive software, but a feature. It's what allows us to make sense of a chaotic universe, to find beauty and meaning in randomness. When we looked at Atlas and saw a future great comet, we were doing what humans have always done, projecting our hopes and dreams onto the cosmic canvas. And for a brief moment, that projection created a shared experience. Around the world, people were united in anticipation. We were all looking up, all looking forward to the same event. In a time of division and isolation, the comet gave us something to share, something to hope for together. That hope, that anticipation, that collective dreaming, wasn't that valuable in itself, regardless of the outcome? Moreover, our misreading led to an intensity of observation that might not have occurred otherwise. Because we thought Atlas would be spectacular, we watched it more closely. We gathered more data. We learned more about it than we might have if we had correctly predicted its demise from the start. Our error led to greater knowledge, our mistake to deeper understanding. This is often how science progresses, not in straight lines, but in spirals, circling back on itself, revising and refining. Every failed prediction is a learning opportunity. Every surprise is a chance to update our models. Atlas taught us about the fragility of dynamically new comets. It showed us that brightness isn't always an indicator of stability. It reminded us that the universe still has the capacity to surprise us, even with all our sophisticated instruments and computational models. The story of Atlas also raises philosophical questions about the nature of observation and reality. Did our watching change what happened? Not in any physical sense. The comet would have fragmented whether we were watching or not. But in a very real sense, our observation created the event. Without human eyes and minds to witness and interpret, Atlas would have been just another chunk of ice dissolving in the void. It was our attention, our hope, our disappointment that transformed it into a story, a moment of meaning in the vast meaninglessness of space. This brings us to a deeper contemplation about our relationship with the cosmos. We are the universe becoming aware of itself. Through our eyes, the cosmos observes its own beauty, its own processes, its own evolution. When we watched Atlas die, it was the universe watching itself transform. We were not separate from the event, but part of it. Our consciousness, our emotions, our interpretations, these are as much a part of the cosmic story as the comet itself. And what a privilege that is. Of all the countless worlds that might exist in our galaxy, our universe, we know of only one where beings have evolved the capacity to look up and wonder, only one where a dying comet can inspire poetry, art, science, philosophy. We are the universe's way of contemplating itself, and every astronomical event we witness is a moment of cosmic self-reflection. Atlas may not have given us the spectacular show we anticipated, but it gave us something perhaps more valuable, a reminder of our place in the cosmic order. We are observers, interpreters, meaning makers. We are the ones who transform mere physical events into stories, into lessons, into beauty. And in that transformation, we add something to the universe that wasn't there before: consciousness, awareness, appreciation. As we move forward in our exploration of Atlas's story, as we delve deeper into the mystery of its nature and meaning, remember this: we are not just learning about a comet. We are learning about ourselves, about our relationship with the cosmos, about the nature of expectation and reality. We are learning that sometimes the most profound truths come not from success, but from failure, not from fulfillment, but from disappointment, not from answers, but from questions. The night sky continues to turn above us. Other comets are falling in from the Oort cloud, each on its own ancient journey. Some will survive their encounter with the sun and become the great comets of the future. Others will follow Atlas's path, dissolving into whispers of dust and gas, and we will be here, watching, waiting, wondering. We will continue to misread and reinterpret, to hope and be disappointed, to project our dreams onto the cosmic canvas. Because that's what we do. That's who we are. We are the dreamers of the universe, and every comet, whether it fulfills our expectations or not, is an invitation to dream. As March 2020 progressed, the astronomical community found itself in an unusual position. We were watching a comet die in real time, something that had rarely been observed with such detail before. Every telescope that could be pointed at ATLAS was doing so. Amateur astronomers were providing nightly updates. Professional observatories were dedicating precious observation time to documenting the disintegration. It was like a cosmic wake, with the global astronomy community serving as mourners and witnesses. The fragmentation process itself was fascinating to observe. It didn't happen all at once, but in stages, like a slow-motion explosion played out over weeks. First, the nucleus elongated, stretching like taffy, then distinct. Condensations appeared within the coma, each representing a fragment of the original nucleus. These fragments continued to separate, some breaking apart further, creating a cascade of disintegration. Each fragment behaved slightly differently. Some brightened as they exposed fresh ice to sunlight. Others faded quickly, exhausting their volatile materials. Some developed their own small tails, miniature comets in their own right. Others simply dissolved into clouds of dust. It was like watching a single firework explode into dozens of smaller fireworks, each with its own pattern and timing. The dynamics of the fragmentation told us about forces we rarely get to observe directly. Solar radiation pressure, the gentle but persistent push of sunlight, was slowly accelerating the smaller fragments away from the sun. The solar wind, that stream of charged particles flowing from our star, was sculpting the gas and dust into complex shapes. Gravitational perturbations from the planets were subtly altering each fragment's orbit. We were watching celestial mechanics in action, a practical demonstration of the forces that shape our solar system. But perhaps the most remarkable thing about the fragmentation was how gentle it was. This wasn't a violent explosion, but a quiet dissolution. The fragments separated at speeds of just a few meters per second, walking pace. If you could have stood on one fragment, you would have seen the others drifting away like boats on a calm sea. There was something deeply peaceful about it, a cosmic letting go. This gentleness told us something important about the nature of comets. They are not solid rocks, but delicate assemblages of ice and dust, held together by the weakest of forces. They are more like cosmic snowflakes than cosmic boulders. And like snowflakes, they are ephemeral, existing only under specific conditions, dissolving when those conditions change. The public reaction to Atlas's fragmentation was mixed. There was disappointment, certainly. The media had hyped the comet extensively, and now had to explain its anticlimactic end. Some people felt cheated, robbed of the celestial spectacle they had been promised. But there was also fascination. The story of a comet dying was, in its own way, as compelling as the story of a comet shining. Death and birth, ending and beginning, destruction and creation. These are the fundamental dramas of existence, played out on every scale from the quantum to the cosmic. Science educators found in Atlas's demise a teaching moment. Here was a real-time demonstration of how science works. We make predictions based on the best available data. Sometimes those predictions are wrong. When they are, we learn from our mistakes and refine our understanding. The comet became a lesson in scientific humility, a reminder that nature doesn't always follow our scripts. Children who had been disappointed by the comet's failure to perform were introduced to a different kind of wonder. They learned about the Oort cloud, that vast reservoir of ancient ice at the edge of our solar system. They learned about the forces that can destroy a mountain-sized object without violence or explosion. They learned that the universe is full of quiet dramas, subtle beauties, gentle mysteries. They learned that not all cosmic events are Hollywood-style spectacles, and that the quiet ones can be just as meaningful. For amateur astronomers, Atlas's fragmentation presented a unique observational challenge. As the comet broke apart, it became fainter and more diffuse, harder to observe. But this difficulty made it more rewarding for those who persisted. Finding and photographing the fragments became a badge of honor in the amateur astronomy community. Those who managed to capture images of the disintegrating comet shared them proudly, contributing to our collective documentation of this rare event. Professional astronomers, meanwhile, were scrambling to gather as much data as possible. Every spectrum, every photometric measurement, every astrometric position was valuable. Papers were being written even as the comet continued to dissolve. Scientific collaborations formed spontaneously, with researchers around the world sharing data and insights. The comet's death became a catalyst for scientific cooperation, bringing together researchers who might never have collaborated otherwise. One of the most intriguing aspects of Atlas's story was its possible connection to historical comets. As astronomers calculated the comet's orbit more precisely, they noticed something remarkable. Its path through the solar system was strikingly similar to that of the Great Comet of 1844, a spectacular comet that had been visible to the naked eye for weeks. Could these two comets be related? Could they be fragments of an even larger parent body that had broken apart centuries or millennia ago? This possibility opened up a new dimension to the story. If Atlas and the 1844 comet were siblings, then we were witnessing not just the death of one comet, but the continuation of an ancient fragmentation cascade. Somewhere in the past, a massive comet had broken apart, sending fragments on similar but slightly different orbits. These fragments would return at different times, each making its own passage through the inner solar system. Some, like the 1844 comet, would survive and put on a show. Others, like ATLS, would dissolve into nothing. This connection to the past added a poignancy to Atlas's story. It wasn't just a random comet that happened to fall apart. It was part of a family, a lineage of cosmic wanderers. Its death was connected to events that happened before any human currently alive was born, possibly before human civilization existed. We were witnessing one chapter in a story that had been unfolding for centuries, maybe millennia. The idea of comet families is not new to astronomy. We know of several groups of comets that share similar orbits, suggesting common origins. The Kreutz sun grazers, for example, are a family of comets that pass extremely close to the Sun. They're all fragments of a single massive comet that broke apart perhaps 2,000 years ago. Every few years, one of these fragments makes its death dive toward the Sun, creating a brief, brilliant display before evaporating in the solar corona. But Atlas's family, if it exists, would be different. These wouldn't be sun grazers, but comets with more distant perihelia, close enough to the Sun to become active but not so close as to guarantee destruction. This would make them more unpredictable. Some family members might survive multiple passages. Others, like ATLAS, might fragment on their first approach. Each return would be a roll of the cosmic dice. The search for other members of Atlas's family has become an ongoing project. Astronomers are combing through historical records, looking for comets with similar orbits. They're also watching for new comets that might be related. If we could identify multiple family members, we could piece together the story of the original parent body. How big was it? When did it fragment? What caused it to break apart? These questions might seem academic, but they speak to fundamental processes that have shaped our solar system. As April 2020 wore on, ATLAS continued to fade. The fragments spread out along the orbital path, becoming harder and harder to observe. By May, when the comet should have been at its brightest, it was barely visible even in the large telescopes. The show was over. The cosmic ghost had fully dissolved into the darkness. But the scientific analysis was just beginning. Data from multiple observatories was being compiled and analysed. Spectra revealed the comet's composition in unprecedented detail. We detected not just water and common gases, but complex organic molecules, the building blocks of life. We measured isotope ratios that told us about the conditions in the early solar system. We tracked the motion of individual fragments, learning about the forces that drove them apart. Every piece of data added to our understanding, not just of Atlas, but of comets in general. One particularly interesting discovery was the detection of unusual molecules in Atlas's coma. Observations revealed the presence of iron and nickel atoms, elements rarely seen in comets at such distances from the Sun. Usually these metals only become detectable when comets pass very close to our star, where temperatures are high enough to vaporize even refractory materials. But Atlas was releasing these atoms while still beyond the orbit of Mars. This suggested that the comet contained these metals in an unusually volatile form, perhaps as organometallic compounds that sublimate at lower temperatures. This discovery had implications beyond just ATLAS. If comets regularly carry such compounds, they could have played a role in delivering not just water and organics to early Earth, but also metals important for life. Iron, for instance, is essential for many biological processes. If comets were a significant source of Earth's iron, it would add another chapter to the story of how our planet became habitable. The study of Atlas's dust was equally revealing. As the comet dissolved, it released enormous quantities of dust into space. This dust was analysed using various techniques, including polarimetry, which measures how light scatters off particles. The results showed that Atlas's dust was unusually fine, with most particles smaller than a micrometer. This fine dust would be easily blown away by solar radiation pressure, spreading throughout the inner solar system. Some of this dust will eventually reach Earth, not as dramatic meteorites, but as a gentle rain of microscopic particles. Every day, Earth accumulates about 100 tons of cosmic dust, most of it from comets and asteroids. Atlas has added its contribution to this cosmic rain. Right now, as you listen to these words, particles that were once part of ATLAS might be settling through our atmosphere, adding their ancient atoms to our world. The distribution of this dust is not uniform. It follows complex patterns determined by orbital mechanics and solar radiation. Some of it will be concentrated along Atlas's orbital path, creating a potential meteor stream. Other particles will be scattered more widely, joining the zodiacal cloud, that diffuse disk of dust that surrounds the Sun. On clear, dark nights, you can sometimes see this cloud as a faint glow along the ecliptic called zodiacal light. Atlas is now part of that glow, its substance transformed into a permanent, if faint, feature of our sky. But dust wasn't the only thing Atlas left behind. The gas released by the comet's sublimation has also dispersed through the solar system. Water vapor, carbon monoxide, carbon dioxide, and dozens of other compounds are now spreading through space. Some of this gas will be ionized by solar radiation, becoming part of the solar wind. Some will be photodissociated, broken apart by ultraviolet light into constituent atoms. These atoms will join the thin interplanetary medium, that near vacuum that fills the space between planets. It's a strange thought, but the space between Earth and Mars is now slightly different because of Atlas. The comet has added its molecules to the mix, changing the composition of interplanetary space in a tiny but measurable way. Future spacecraft travelling to Mars will fly through gas that was once part of ATLAS. In a very real sense, the comet has become part of the architecture of our solar system. This transformation from solid object to dispersed gas and dust is the fate of all comets. It's estimated that the solar system loses about 10 to 20 comets per year to complete dissolution. Over the age of the solar system, that's millions of comets. All that material doesn't disappear, it just changes form. It becomes part of the solar wind, part of planetary atmospheres, part of the zodiacal dust, cloud. Comets are slowly painting the solar system with their substance, adding layers of material like an artist, adding layers of paint to a canvas. This process has been going on since the solar system formed. In fact, it was probably more intense in the early days, when there were more comets, and the young sun was more active. Early Earth was bombarded by comets at a rate thousands of times higher than today. These impacts delivered vast quantities of water and organic compounds, possibly providing the raw materials for life. We are, in a very literal sense, the children of comets, but comets don't just bring material to planets, they also tell us about conditions in the early solar system. Each comet is a time capsule, preserving information about the environment in which it formed. By studying comets like ATLAS, we can peer back in time to the solar system's infancy. The isotope ratios in cometary water tell us about the temperature at which the ice formed. The presence of certain molecules tells us about the chemical processes that were occurring. The structure of the nucleus tells us about the accretion process that built the first solid bodies. Atlas in particular told us about the outer reaches of the early solar system. Its composition suggested it formed in a region where temperatures were below 30 Kelvin, cold enough for even carbon monoxide to freeze. This places its birthplace far beyond Neptune, in the realm where the solar nebula was transitioning into interstellar space. The comet was a messenger from the edge. carrying information about conditions at the very boundary of our solar system. The fragility that led to Atlas's destruction was itself informative. It told us that some comets form through very gentle accretion, with particles slowly accumulating under minimal gravity. These rubble-pile comets are held together by forces barely stronger than the static electricity that makes dust cling to your television screen. They are the cosmic equivalent of dust bunnies, accumulations of particles that have never been compressed or consolidated. This gentle formation process preserves the original structure and composition of the solar nebula. Unlike planets, which have been melted, differentiated, and processed by geological activity, these comets are pristine samples of the primordial material. When Atlas fell apart, it was like opening a 4-billion-year-old sample container, releasing material that had been unchanged since the dawn of the solar system. The scientific value of this cannot be overstated. While we have sent spacecraft to several comets, even returning samples from one, each comet we study adds to our understanding. Atlas, despite or perhaps because of its fragmentation, provided unique insights. Its complete dissolution allowed us to study material from throughout the nucleus, not just the surface. We saw the comet's interior, something that intact comets rarely reveal. As spring turned to summer in 2020, Atlas faded from the headlines. Other events, more pressing and terrestrial, demanded attention. But in observatories and research institutions around the world, the work continued. Papers were written, conferences were held, debates were engaged. The comet might have dissolved, but its scientific legacy was just beginning to solidify. One of the ongoing debates centered on the exact mechanism of Atlas's fragmentation. While thermal stress from solar heating was the most likely cause, other possibilities were considered. Could the comet have been spinning too fast, torn apart by centrifugal force? Could it have been hit by a small meteoroid, shattering its already fragile structure? Could tidal forces, though weak at the comet's distance from the Sun, have played a role? Each hypothesis had its proponents, and the debate continues. Another area of investigation was the comet's rotation. Before it fragmented, ATLAS was observed to be rotating with a period of about 8 hours. But this rotation was not stable. The period was changing, sometimes speeding up, sometimes slowing down. This chaotic rotation was likely caused by jets of gas acting like thrusters, pushing the comet in different directions. As the jets turned on and off with the comet's rotation, they created a complex pattern of forces that made the rotation increasingly unstable. This rotational instability might have contributed to the fragmentation. As the comet spun faster, centrifugal forces would have increased, potentially exceeding the weak gravitational and cohesive forces holding the nucleus together. It's possible that Atlas literally spun itself apart, like a figure skater spinning so fast they lose their balance and fall. The study of Atlas's fragments revealed another interesting phenomenon. They didn't all behave the same way. Some fragments continued to brighten after separation, suggesting they contained pockets of particularly volatile ice. Others faded immediately, apparently exhausted of sublimating material. This heterogeneity told us that the original nucleus was not uniform but had a complex internal structure, with regions of different composition and volatility. This complexity is important for understanding how comets form. If comets were simple, homogeneous balls of ice and dust, we would expect them to behave predictably. But the reality is far more interesting. Comets are complex, heterogeneous objects with intricate internal structures. They are more like cosmic geology than cosmic snowballs, with layers, veins, and pockets of different materials. Imagine the original Atlas nucleus as a cosmic parfait, with layers of different ices and dust laid down at different times during its formation. As the comet accreted in the outer solar system, it would have incorporated material from different regions, each with its own composition. Some layers might be rich in water ice, others in carbon monoxide or methane. Some might contain more dust, others might be nearly pure ice. This layered structure would make the comet's behavior complex and unpredictable. When such a structured object is heated by the sun, the results can be dramatic. Different ices sublimate at different temperatures. Water ice needs relatively high temperatures, while carbon monoxide can sublimate even in the outer solar system. As the comet approaches the sun, these different ices activate in sequence, creating a complex pattern of outgassing. If the structure is layered, the activation of a volatile layer could literally blow off the overlying material, exposing fresh ice and accelerating the sublimation. This is likely what happened to ATLS. As it approached the sun, increasingly volatile ices began to sublimate. The gas pressure built up within the nucleus until it exceeded the strength of the overlying material. Cracks formed, propagated, and eventually split the nucleus apart. Each fragment then evolved independently, its fate determined by its particular composition and structure. The story of ATLAS thus becomes a lesson in cosmic complexity. We like to think of celestial objects as simple, governed by basic physical laws, and they are, at a fundamental level. But the expression of those laws in real objects can be incredibly complex. A comet is not just a ball of ice orbiting the sun. It's a complex system with its own internal dynamics, its own history, its own unique character. Understanding comets means appreciating this complexity, embracing the unpredictability, accepting that each comet is an individual with its own story to tell. As we continue our journey into the mystery of Comet ATLAS, we must step back from the specific story of this one comet and consider the broader canvas upon which it painted its brief existence. To truly understand what happened to ATLAS, to grasp why it behaved as it did, and what its dissolution means, we need to understand the fundamental nature of these cosmic wanderers. What are comets, really? Where do they come from? What forces shape their existence? And why are some, like Atlas, so extraordinarily fragile that they cannot survive even a single passage through the inner solar system? The story of comets is the story of ice and time. It's a story that begins in the cold, dark spaces between the stars, in the vast molecular clouds where new solar systems are born. When our own solar system was forming 4.5 billion years ago, it began as just such a cloud, a region of slightly denser gas and dust within the spiral arm of our galaxy. This cloud, perhaps triggered by the shock wave from a nearby supernova, began to collapse under its own gravity. As it collapsed, it spun faster, like a figure skater pulling in their arms. The center grew hot and dense, eventually igniting as our sun. But not all the material fell into the center. Some remained in orbit, forming a disk of gas and dust around the young star. In this disk, temperature decreased with distance from the sun, close in, where Mercury, Venus, Earth, and Mars would form. It was hot enough that only rocky materials could condense. Water, methane, ammonia, and other volatile compounds remained as vapor. But farther out, beyond what astronomers call the frost line, it was cold enough for these volatiles to freeze. This is where the giant planets formed, their massive cores of ice and rock, able to capture and hold vast atmospheres of hydrogen and helium. And beyond even the giant planets, in the cold, dark reaches of the outer disk, countless small bodies formed from the leftover material. These bodies, composed primarily of ice with some rock and dust mixed in, are what we call comets. But not all comets remained where they formed. The gravitational influence of the giant planets, particularly Jupiter and Neptune, scattered many of these icy bodies. Some were flung inward, where they collided with the forming terrestrial planets or fell into the sun. Others were thrown outward, into highly elliptical orbits that took them far from the sun. And some were ejected entirely from the solar system, becoming interstellar wanderers. Those that remained bound to the sun but were scattered to great distances formed what we now call the Oort cloud, that vast spherical shell of icy bodies that extends perhaps a quarter of the way to the nearest star. The Oort cloud is a place of profound cold and darkness. The sun, from that distance, is just another star, albeit the brightest one. Temperatures hover just a few degrees above absolute zero. Time seems to slow down. Orbits that take millions of years are the norm. The icy bodies drift in this cosmic deep freeze, perfectly preserved relics of the solar system's formation. They are, in essence, time capsules, waiting to be opened. Occasionally something disturbs these sleeping giants. A passing star, the gravitational tide of the galaxy, or even the slow chaotic evolution of their orbits can nudge an Oort cloud object onto a new path. Instead of circling endlessly in the dark, it begins to fall toward the sun. This journey can take millions of years, a slow, patient spiral through the outer solar system. As the comet falls, it gradually picks up speed, trading gravitational potential energy for kinetic energy. By the time it reaches the orbit of Neptune, it's moving at several kilometers per second. By Jupiter's orbit, it's really cooking. And as it approaches the inner solar system, where Earth orbits, it's screaming along at tens of kilometers per second. But speed isn't the only thing that changes as a comet approaches the sun. Temperature changes too, and this is where the magic happens. Remember, comets are made primarily of ice, not just water ice, but frozen carbon dioxide, carbon monoxide, methane, ammonia, and dozens of other compounds. Each of these ices has its own sublimation temperature, the point at which it transforms directly from solid to gas. As the comet warms, these ices begin to activate in sequence. Carbon, monoxide and methane might start sublimating beyond the orbit of Jupiter. Carbon dioxide kicks in around Mars's orbit. Water ice, the most abundant component, really gets going inside Earth's orbit. When these ices sublimate, they don't do so uniformly. The sun-facing side of the comet gets warmer than the night side, creating temperature differences that can exceed 100 degrees. This uneven heating causes the ice to sublimate more rapidly on the sunlit side, creating jets of gas that shoot out from the nucleus. These jets carry dust with them, tiny particles that were embedded in the ice. As the gas expands into the vacuum of space, it forms the comet's coma, that fuzzy cloud that can grow larger than Jupiter. The dust, pushed by radiation pressure and shaped by the solar wind, forms the comet's tail, that beautiful banner that can stretch for millions of kilometers. This is the classic picture of a comet, the one we all learn in school. But the reality is far more complex and interesting. Each comet is unique, its behavior determined by its particular composition, structure, and history. Some comets are rock hard, consolidated by eons of cosmic ray bombardment. Others are fluffy and porous, more empty space than solid material. Some are rich in water ice, others in more exotic compounds. Some are pristine, visiting the inner solar system for the first time. Others are veterans, their volatile ices long since depleted by repeated passages near the sun. Atlas belong to the most interesting category, the dynamically new comets. These are comets making their first journey from the Oort cloud to the inner solar system. They have never before experienced the sun's warmth, never before been subjected to the stresses of rapid heating and cooling. They are, in the truest sense, pristine samples of the early solar system, but this pristine nature comes with a price. These comets have not been consolidated by repeated heating. Their structure is often extremely fragile, held together by forces barely stronger than those that hold a sandcastle together. To understand just how fragile, we need to think about how these comets formed in the first place. In the outer regions of the protoplanetary disk, where temperatures were extremely low, ice crystals formed and grew. These crystals collided gently, sticking together through a combination of van der Waals forces, the weak electrical attractions between molecules, and sintering, a process where ice crystals slowly fuse at their contact points. The process was extraordinarily gentle. Collision speeds were measured in centimeters per second, not kilometers. The growing cometesimals, as they're called, were more like cosmic dust bunnies than solid rocks. As these fluffy aggregates grew, their own gravity became important. But even then, the forces involved were minimal. A comet nucleus a few kilometers across has a surface gravity thousands of times weaker than Earth's. You could easily jump off such a body and never come back. This weak gravity means that the material making up the comet is barely compressed. The interior remains porous and fragile, a loosely bound collection of smaller pieces rather than a solid, monolithic body. This structure has profound implications for what happens when such a comet approaches the Sun. As the surface heats up and ices begin to sublimate, the gas doesn't just flow smoothly off the surface. It has to work its way through the porous interior, building up pressure in voids and cracks. If the pressure exceeds the tensile strength of the material, which isn't very high to begin with, the comet can literally blow itself apart. It's like a pressure cooker with no safety valve. Eventually something has to give. This is likely what happened to ATLAS. As it approached the Sun, its ancient ices began to awaken. Carbon monoxide, frozen for billions of years, suddenly found itself warm enough to sublimate. The gas built up pressure within the nucleus, seeking any weakness, any crack or void through which to escape. The comet's fragile structure, which had survived for eons in the cold and dark, couldn't withstand these new stresses. Cracks propagated through the nucleus like fractures through thin ice. And eventually, catastrophically but also gently, the comet came apart. The process of cometary fragmentation is one of the most fascinating phenomena in solar system dynamics. It's not like an explosion in the traditional sense. There's no sudden release of energy, no violent shattering. Instead, it's more like a slow-motion dissolution, a gentle drifting apart. The fragments separate at speeds of just a few meters per second, barely faster than walking pace. If you could stand on one fragment, you would see the others slowly receding, like boats drifting apart on a calm lake. This gentle separation tells us something important about the forces involved. The energy breaking the comet apart isn't coming from some violent event, but from the slow, steady pressure of sublimating gas. It's a patient force building up over weeks or months until the comet's structure simply can't contain it anymore. When the break finally comes, it's almost peaceful, a quiet acknowledgement that the forces of dissolution have overcome the forces of cohesion. But why are some comets so much more fragile than others? Why did Atlas fall apart while other comets, like Halley's, survive passage after passage? The answer lies in their history. Comets that have survived multiple passages near the Sun have been processed. Their volatile ices have been depleted from the outer layers, leaving behind a lag deposit of dust that insulates the interior. The repeated heating and cooling has consolidated the structure, sintering the ice crystals together more firmly. These processed comets are tougher, more resilient, better able to withstand the stresses of solar approach. Dynamically, new comets like ATLAS have none of these advantages. They're volatile. Ices extend all the way to the surface. Their structure has never been consolidated by heating. They're experiencing stresses they've never felt before, and they have no evolutionary adaptation to help them cope. They are like deep-sea creatures suddenly brought to the surface, unable to survive the change in pressure. The very thing that makes them scientifically valuable, their pristine nature, also makes them vulnerable to destruction. The composition of ATLAS, revealed through spectroscopic observations, was particularly interesting. The comet showed strong emissions from molecules like C2, diatomic carbon, and CN, cyanogen, giving it that distinctive green color. But it also showed unusually strong emissions from CO, indicating that this volatile ice made up a significant fraction of the nucleus. Carbon monoxide ice is particularly problematic for cometary stability. It sublimates at much lower temperatures than water ice, meaning it becomes active much farther from the Sun. This early activation can destabilize a comet's nucleus long before it reaches the inner solar system. Think of the comet nucleus as a complex mixture of different ices, each with its own personality. Water ice is the stable one, needing relatively high temperatures to sublimate. It forms the backbone of most comets. Carbon dioxide is more volatile, creating problems at moderate distances from the Sun. Carbon monoxide is the troublemaker, active even in the outer solar system. Methane and ammonia add their own complications, and mixed throughout are organic molecules, complex carbon-based compounds that can include everything from simple hydrocarbons to amino acids, the building blocks of life. This chemical complexity means that as a comet approaches the Sun, it doesn't just turn on like a light switch. Instead, different regions activate at different times, depending on their composition and their exposure to sunlight. A pocket of carbon monoxide ice might start out gassing while surrounding water. Ice remains frozen. This creates differential stresses within the nucleus, like having one part of a structure expanding while another remains static. These stresses can create cracks, which allow gas to escape more easily, which increases the sublimation rate, which creates more stress. It's a positive feedback loop that can quickly lead to fragmentation. The organic molecules in comets add another layer of complexity. These aren't just simple compounds, but can include complex polymers and macromolecules. Some of these organics are created in the interstellar medium, formed by radiation processing of simpler molecules. Others form within the comet itself, as cosmic rays trigger chemical reactions in the ice. These organics can affect the comet's behavior in unexpected ways. They can create a dark, insulating crust that affects how heat penetrates the nucleus. They can act as binding agents, holding dust particles together. Or they can create weak zones that become failure points under stress. Atlas showed evidence of complex organics in its spectrum. The green color came from C2, but there were also signatures of more complex carbon chains. These molecules tell us about the chemical processes that occurred in the outer solar system billions of years ago. They're evidence of a rich chemistry that preceded life on Earth, a chemistry that might have contributed to life's emergence. Every comet that falls apart in the inner solar system is seeding space with these organic molecules, continuing a process that has been going on since the solar system formed. The dust released by Atlas was equally interesting. Cometary dust isn't like the dust in your house. It's a mixture of minerals that formed at high temperatures in the inner solar system and were somehow transported outward, and ices and organics that formed in the cold of the outer system. Some dust grains are pristine interstellar particles, older than the solar system itself. Others are aggregates that formed within the solar nebula. Each grain has its own story, its own history of formation and processing. When Atlas fragmented, it released enormous quantities of this dust. Observations showed that the dust production increased dramatically during the fragmentation events, as fresh material was exposed to sunlight. This dust didn't just disappear, it continues to orbit the Sun, spreading out along Atlas's orbital path. Some of it will spiral inward, eventually reaching Earth's orbit. When it does, it will enter our atmosphere as meteors, those brief streaks of light we call shooting stars. The dust from ATLAS will continue to arrive at Earth for decades, maybe centuries, a gentle rain of ancient material from the edge of the solar system. The study of this dust, even from a distance, revealed interesting patterns. The dust grains from Atlas were unusually small, most less than a micrometer across. This fine dust is easily pushed around by radiation pressure, the gentle but persistent force of sunlight. As a result, the dust tail of Atlas showed complex structures, with striations and synchrones that revealed the size distribution of the particles. It was like reading a book written in dust, each feature telling us something about the comet's composition and how it was falling apart. The gas released by ATLAS was equally informative. As the various ices sublimated, they released their characteristic molecules into space. Water vapor, of course, was abundant. But so were carbon monoxide, carbon dioxide, methane, ammonia, and dozens of other species. Each molecule has its own spectroscopic signature, its own unique pattern of absorption and emission lines. By analysing the comet's spectrum, astronomers could determine not just what molecules were present, but their relative abundances and temperatures. One particularly interesting discovery was the detection of hypervolatile species, molecules that sublimate at extremely low temperatures. These included species like carbon monoxide and methane, but also more exotic molecules like formaldehyde and methanol. The presence of these hypervolatiles in significant quantities confirmed that ATLAS was indeed a dynamically new comet, fresh from the Oort cloud. A comet that had made previous passages would have lost these volatile species from at least its outer layers. The isotope ratios in Atlas's gases provided another window into the past. Isotopes are versions of elements with different numbers of neutrons. For example, most hydrogen has no neutrons, but deuterium, or heavy hydrogen, has one. The ratio of deuterium to regular hydrogen in cometary water tells us about the temperature at which that water formed. Atlas showed a deuterium to hydrogen ratio about twice that of Earth's oceans, suggesting its ice formed at very low temperatures, probably below 30 Kelvin. This places its formation in the outer reaches of the protoplanetary disk, or even in the interstellar medium before the solar system formed. The carbon isotope ratios told a similar story. The ratio of carbon-13 to carbon-12 in Atlas's molecules was consistent with formation in a very cold environment, where certain chemical reactions that fractionate isotopes proceed differently than at higher temperatures. These isotopic signatures are like fingerprints, unique identifiers that tell us where and when the comet's materials formed. They connect Atlas to the broader story of solar system formation, showing how material was distributed and processed in the early nebula. As we delve deeper into the nature of comets like ATLAS, we begin to see them not as simple dirty snowballs, but as complex chemical laboratories. Within their icy matrices, a rich chemistry has been occurring for billions of years. Cosmic rays trigger reactions that create new molecules. Radioactive decay provides gentle heating that allows molecules to migrate and react. The very slow warming as a comet falls toward the sun activates different chemical pathways. By the time a comet becomes visible from Earth, it's not just releasing stored molecules, but also products of billions of years of slow chemical evolution. This chemical evolution is particularly important for understanding the role comets might have played in the origin of life. Comets contain many of the molecules necessary for life. Water, of course, but also amino acids, the building blocks of proteins, nucleobases, components of DNA and RNA, and lipids, which form cell membranes. When comets impact planets, or when their dust settles gently through an atmosphere, they deliver these prebiotic molecules. It's possible, even likely, that comets played a crucial role in making Earth habitable, and perhaps even in sparking the chemical reactions that led to the first life. A TLAS, in its brief appearance and dramatic dissolution, contributed to this ongoing delivery. The organic molecules it released will eventually find their way to planets throughout the inner solar system. Some will be destroyed by solar radiation, others will be swept up by the solar wind and carried to the outer system, but some will survive, adding their chemical complexity to the inventory of whatever worlds they encounter. In this way, comets like ATLAS are part of a vast, slow process of chemical exchange within the solar system, a process that has been going on for billions of years and will continue for billions more. The fragility that led to Atlas's destruction is, from this perspective, not a weakness, but a feature. If comets were too tough, if they survived passage after passage without releasing material, they would be less effective at distributing their chemical cargo. The fact that many comets, especially dynamically new ones, fragment and dissolve means that their material is more efficiently spread throughout the solar system. Each fragmentation event is like opening a treasure chest, releasing ancient materials that have been locked away since the dawn of time. This brings us to a profound realization about the nature of our solar system. It's not a static arrangement of planets orbiting a star, but a dynamic, evolving system where material is constantly being exchanged, recycled, and transformed. Comets are key players in this cosmic recycling program. They store material in the deep freeze of the outer system, then release it during brief visits to the inner system. They're like a circulatory system for the solar system, moving materials from the cold periphery to the warm center and sometimes back again. The story of Atlas is just one chapter in this larger story. Its formation billions of years ago, its long hibernation in the Oort cloud, its brief journey to the inner system, and its ultimate dissolution are all part of the normal life cycle of comets. What made Atlas special wasn't that it fell apart, but that we were watching when it did. We caught it in the act of transformation, witnessed its metamorphosis from solid body to dispersed cloud. We saw the moment when billions of years of stored history was released into space. As we studied Atlas's remains, we found evidence of an even deeper connection to the past. The orbit of Atlas was remarkably similar to that of the Great Comet of 1844, a spectacular naked-eye comet that graced Earth's skies in the mid-19th century. The similarity was too close to be coincidence. The two comets must be related, fragments of a larger parent body that broke apart sometime in the past. This connection opened up a new dimension to the Atlas story, linking it not just to the ancient past of the solar system, but to human history as well. The Great Comet of 1844 was one of the most impressive comets of the 19th century. It was discovered in December 1844 and remained visible to the naked eye for several months. At its peak, it sported a tail that stretched across a significant portion of the sky. It was observed by astronomers around the world, painted by artists, and written about by poets. It was in many ways the Atlas that might have been, the spectacular show that we had hoped for in 2020. But the 1844 Comet and Atlas were siblings, not twins. They shared a common origin, but had different fates. The 1844 Comet survived its passage near the Sun, putting on its spectacular show before retreating back to the outer system. Atlas, perhaps smaller or more fragile, couldn't survive the same journey. The difference in their fates tells us about the diversity even within cometary families. Each fragment of the original parent body had its own composition, structure, and destiny. The existence of this cometary family raises fascinating questions. How many other fragments are out there? When did the original parent body break apart? What caused the fragmentation? Was it a collision with another body? Thermal stress from a previous solar passage? Or perhaps the parent body was so large and loosely bound that it simply fell apart under its own weight. These questions connect Atlas to a larger story, a multi-generational saga playing out over centuries or millennia. Astronomers have begun searching for other members of this family. By looking for comets with similar orbital elements, they hope to identify siblings of ATLAS and the 1844 comet. Each new family member discovered would add another piece to the puzzle, helping us reconstruct the story of the original parent body. It's like genealogy, but for comets, tracing family trees back through time to understand the relationships between these cosmic wanderers. The concept of cometary families is well established in astronomy. The most famous is probably the Kreutz-Sungrazer family, a group of comets that pass extremely close to the Sun. These comets are all fragments of a single massive comet that broke apart perhaps 2,000 years ago. Every few years, one of these fragments makes its death dive toward the Sun, creating a brief but spectacular display. Some survive the encounter, though diminished. Others are completely vaporized, their material absorbed into the solar corona. But the Atlas family appears to be different. These aren't sun grazers, but have more distant perihelia. This means they experience less extreme heating and might have better chances of survival. But it also means they're harder to predict. A sun grazer's fate is largely sealed by its close approach to the Sun. but comets like A, T, L, A, S, passing at more moderate distances, can have various outcomes depending on their specific composition and structure. The identification of cometary families has important implications for understanding the Oort cloud. If many comets are fragments of larger parent bodies, it suggests that the Oort cloud contains or contained some very large objects, perhaps hundreds of kilometers across. These massive comets would be more like small planets than traditional comets. Their fragmentation over time would produce families of smaller comets, each carrying part of the parent's material and orbital signature. This hierarchical structure, large parent bodies fragmenting into families of smaller comets, adds complexity to our picture of the Oort cloud. It's not just a collection of independent small bodies, but a structured system with families and relationships. Some regions might be dominated by the descendants of a single massive parent. Other regions might contain more diverse populations. Understanding this structure helps us piece together the formation and evolution of the outer solar system. The fragmentation cascade doesn't stop with the first generation. The fragments themselves can break apart, creating subfamilies, and those fragments can fragment further, creating a fractal pattern of division that continues until the pieces are too small to survive or all the volatile material has been lost. Atlas might itself have been a second or third generation fragment, a piece of the original parent body. Its fragility might have been inherited from previous fragmentation events that left it barely held together. This multi-generational fragmentation process means that comets can preserve information not just about the early solar system, but about their own family history. The composition of Atlas might tell us not just about conditions in the protoplanetary disk, but about the composition of its parent body and the process that broke it apart. Each comet is thus a nested set of stories, each layer revealing something about a different epoch in solar system history. As we consider the relationship between Atlas and the Great Comet of 1844, we're reminded of the role of chance in astronomical observations. The 1844 comet was discovered and observed with 19th century technology. Visual observations, hand-drawn sketches, and basic photographic plates. Atlas was discovered and studied with 21st century technology, digital cameras, space telescopes, and sophisticated spectrographs. The difference in our observational capabilities means we know far more about Atlas, despite its fainter appearance, than was ever known about its spectacular sibling. This technological progress has transformed our understanding of comets. Where once we could only observe them as fuzzy patches of light, we can now determine their composition, structure, rotation, and evolution in exquisite detail. We can watch them fragment in real time, track individual pieces as they separate, and analyze the gas and dust they release. Every comet observed with modern instruments adds exponentially more to our knowledge than centuries of historical observations. Yet there's something poignant about the contrast between the two sibling comets. The 1844 comet was seen by millions of people with their naked eyes. It was a shared global experience, a celestial event that brought people together in wonder. Atlas, despite being followed by more people than any comet in history thanks to the internet, remained invisible to most. It was a comet for the digital age, experienced primarily through screens rather than direct observation. The immediacy, the visceral connection to the cosmos that the 1844 comet provided, was largely absent from Atlas's story. This technological mediation of our cosmic experiences brings us to a deeper question about Atlas and our interpretation of its journey. As we sit here, contemplating this comet that promised so much and delivered something entirely different, we must turn our gaze inward and ask ourselves, did we see Atlas as it truly was, or did we see what we wanted to see? Were we reading the cosmic signs correctly, or were we projecting our own hopes and expectations onto an indifferent universe? The story of Atlas becomes not just about a comet, but about us, about how we perceive and interpret the cosmos, about the very nature of observation and understanding. Consider for a moment the peculiar position we find ourselves in as conscious beings trying to understand an unconscious universe. We are pattern-seeking creatures, evolved to find meaning and connection in the world around us. This ability served our ancestors well, helping them survive in a dangerous world. The rustle in the grass might be just wind, but assuming it's a predator and being wrong costs nothing, while assuming it's wind and being wrong costs everything. We are descendants of those who saw patterns, who made connections, who found meaning even where none might exist. This pattern-seeking nature extends to our observation of the cosmos. When we look at the stars, we see constellations, even though the stars have no actual connection to each other. When we observe planetary motions, we seek harmonies and resonances. And when we discovered Atlas, we immediately began constructing a narrative. It was brightening rapidly, therefore it would continue to brighten. It was following a certain trajectory of luminosity, therefore it would become a great comet. We took limited data and extrapolated a story, a future, a promise. But the universe doesn't tell stories. It simply is. The brightening of Atlas wasn't a promise of future glory, but simply the result of volatile ices sublimating under solar radiation. The comet wasn't trying to become a great comet. It was just following the laws of physics. The narrative, the expectation, the disappointment, these were entirely human additions to the raw facts of orbital mechanics and thermodynamics. We were reading a story that wasn't actually being told. This raises profound questions about the nature of scientific observation itself. Science prides itself on objectivity, on seeing things as they truly are rather than as we wish them to be. But complete objectivity is impossible. Every observation is filtered through human consciousness, interpreted by human minds, contextualized by human experience. When astronomers first noticed Atlas brightening rapidly, they compared it to other comets they had observed. They used mental models built from previous experiences. They couldn't help but see Atlas through the lens of what they already knew and expected. The history of astronomy is full of such examples where human expectations colored observations. Percival Lowell saw canals on Mars because he expected to find evidence of Martian civilization. Giovanni Schiaparelli saw channels, canali in Italian, which Lowell misinterpreted as artificial canals. For decades, astronomers drew detailed maps of Martian canals that we now know never existed. They weren't lying or deliberately deceiving. They were seeing what they expected to see, their observations shaped by their preconceptions. With Atlas, we perhaps fell into a similar trap, though more subtle. We didn't see things that weren't there, but we interpreted what we saw through the lens of hope and expectation. The rapid brightening that was actually a sign of the comet's fragility was seen as a sign of its vigor. The expanding coma that indicated material being lost at an unsustainable rate was celebrated as a sign of the comet's power. We saw what we wanted to see, a cosmic spectacle in the making. This human element in observation is not necessarily a flaw. It's part of what makes us human, what drives us to explore and understand. The excitement generated by Atlas's potential led to intense observation that might not have occurred otherwise. Amateur astronomers around the world turned their telescopes toward this faint smudge of light. Professional astronomers dedicated valuable telescope time to studying it. The anticipation, even if ultimately unfounded, led to a wealth of scientific data. Moreover, our emotional investment in cosmic events like ATLAS connects us to the universe in a way that pure objectivity never could. When we hope for a great comet, when we feel disappointment at its dissolution, we are engaging with the cosmos not just intellectually but emotionally. We are making it part of our human story, weaving it into the narrative of our lives. This emotional connection might not be scientific, but it's profoundly meaningful. It's what transforms astronomy from a dry catalogue of facts into a source of wonder and inspiration. The story of Atlas also highlights how our technological mediation of astronomical events affects our perception. In 1844, when Atlas's sibling comet appeared, people experienced it directly. They walked outside, looked up, and saw it with their own eyes. The comet was part of their sensory experience, as real and immediate as the moon or the stars. But Atlas was experienced primarily through screens, through processed images and data visualizations. Even those who observed it through telescopes were seeing it through layers of optical and digital processing. This mediation creates a distance between us and the cosmic events we observe. We see images of ATLAS, not ATLAS itself. We read about its spectrum, its composition, its fragmentation, but we don't experience these things directly. The comet becomes an abstraction, a collection of data points and pixels rather than a visceral reality. This abstraction makes it easier to project our expectations onto it. When we're not seeing something directly, it's easier to see what we expect rather than what's actually there. Yet this same technological mediation allows us to see things that would be impossible to perceive directly. The Hubble Space Telescope revealed details of Atlas's fragmentation that no Earth-based observer could have seen. Spectroscopic analysis told us about molecules that emit light invisible to human eyes. Radio observations revealed emissions we couldn't hear. In a sense, our instruments allow us to see Atlas more truly than our eyes ever could. But this enhanced vision comes at the cost of immediacy and direct experience. The question of whether we misread Atlas from the beginning thus becomes more complex. In one sense, yes, we misread it. We interpreted its brightening as a sign of future spectacular visibility, when it was actually a sign of impending dissolution. We projected our hopes onto an indifferent piece of ice and rock, but in another sense, our reading of ATLAS was perfectly valid. We saw in it the potential for wonder, for shared experience, for connection to the cosmos. That these things manifested differently than expected doesn't make our reading wrong, just incomplete. Perhaps the real lesson of ATLAS is that the universe always exceeds our ability to fully comprehend or predict it. No matter how sophisticated our instruments, how complex our models, how vast our databases, the cosmos retains the capacity to surprise us. Atlas reminded us that we don't have everything figured out, that there are still mysteries to uncover, still phenomena we don't fully understand. In an age when it can seem like science has answered all the big questions, Atlas was a humbling reminder of how much we still don't know. This humility is valuable, even necessary. It keeps science honest, prevents it from becoming dogma. Every failed prediction, every surprise, every comet that doesn't behave as expected is an opportunity to refine our understanding, to update our models, to get closer to the truth. Atlas's fragmentation taught us about the fragility of dynamically new comets. Its rapid brightening and subsequent fading refined our understanding of cometary outbursts. Its connection to the 1844 comet opened new avenues for studying cometary families. Even in disappointing us, Atlas advanced our knowledge. But beyond the scientific lessons, Atlas offered philosophical ones. It reminded us that the universe is not here for our entertainment. It doesn't owe us spectacular comets or dramatic celestial events. It simply follows its own rules, indifferent to our hopes and expectations. This might seem cold, even nihilistic, but there's also something liberating about it. We don't have to read meaning into every cosmic event. We can simply observe, appreciate, and learn without the burden of interpretation. At the same time, our human tendency to find meaning, to tell stories, to project hopes onto the cosmos, is itself a remarkable phenomenon. We are, as far as we know, the only beings in the universe capable of this kind of meaning-making. When we looked at Atlas and saw potential for wonder, we were exercising a capacity that might be unique in all the cosmos. Our misreading, if that's what it was a profoundly human act, a demonstration of consciousness engaging with the unconscious universe. This brings us to an even deeper contemplation. When we observe comets like ATLAS, we are not just gathering data about ice and rock. We are participating in a cosmic process of self-awareness. We are the universe observing itself, trying to understand itself. Every spectrum we analyze, every orbit we calculate, every fragmentation we witness is the cosmos learning about its own nature through us. We are not separate from the universe we observe, but part of it, the part that has developed the capacity for observation and understanding. From this perspective, our emotional response to Atlas, our hopes and disappointments, are as much a part of the cosmic story as the comet's physical dissolution. The universe, through us, experienced anticipation and loss. It felt the excitement of discovery and the poignancy of destruction. These feelings might seem insignificant compared to the vast scales of space and time, but they represent something extraordinary. Matter, organized in such a way that it can feel, think, and wonder about itself. The data we collected from ATLAS will be analyzed for years, perhaps decades. Scientists will write papers, refine models, develop new theories. But beyond the scientific value, Atlas gave us something else, a shared moment of attention. For a few months in 2020, people around the world were united in watching this small, distant object. In a time of global challenges and isolation, Atlas provided a point of common focus, a reminder that we all share the same sky, the same cosmic neighborhood. This shared attention is itself a form of meaning-making. When millions of people simultaneously focus on the same cosmic event, they create a collective experience that transcends individual observation. Atlas became part of our collective consciousness, a shared reference point in the human story. Even its failure to meet expectations became a shared experience, a collective lesson in the unpredictability of nature. As we continue to contemplate Atlas and what it means, we must also consider what it left behind. The comet might be gone, but its legacy continues. The dust and gas it released are still traveling through the solar system. Some of that material will eventually reach Earth, adding its ancient atoms to our world. In a very real sense, ATLAS will become part of Earth, part of us. The carbon atoms that once were part of the comet might one day be incorporated into living things, perhaps even into future humans who will look up at the sky and wonder about comets. This material legacy connects us to the deep history of the solar system. Every atom in our bodies, except for hydrogen, was forged in the nuclear furnaces of stars. These atoms were dispersed through space by stellar winds and supernovae, eventually condensing into new stars and planets. Comets like ATLAS are part of this cosmic recycling system, carrying material from the outer reaches of the solar system to the inner planets. When Atlas dissolved, it was continuing a process that has been going on for billions of years and made life on Earth possible. But Atlas's legacy extends beyond the merely material. The observations we made, the data we collected, the lessons we learned will inform future comet studies. When the next dynamically new comet is discovered, astronomers will remember ATLAS. They will be more cautious in their predictions, more aware of the possibility of fragmentation. Atlas has become part of the accumulated wisdom of astronomy, a cautionary tale and a valuable case study. The story of Atlas also contributes to our cultural understanding of comets and our place in the cosmos. Every generation has its memorable comets, celestial events that become part of the cultural fabric. For some, it was Halley's Comet in 1986 or Hale-Bopp in 1997. For others, it might be Atlas, not for its spectacular appearance, but for its profound lesson in cosmic humility. Atlas taught us that the universe can still surprise us, that our expectations can be confounded, that beauty can be found in dissolution as well as in spectacle. As we delve deeper into what Atlas means, we must confront the fact that meaning itself is a human construction. The universe doesn't mean anything, it simply is. But we are meaning-making creatures, and we cannot help but find significance in cosmic events. This is not a weakness or a delusion, but perhaps our greatest strength. Through our meaning-making, we transform the raw material of existence into something more: stories, lessons, connections, understanding. The question, did we misread Atlas from the beginning? Thus has multiple answers depending on the level at which we examine it. Scientifically, yes, we misinterpreted the data and made incorrect predictions. But humanly, culturally, philosophically, our reading of Atlas was rich and complex, full of hope and wonder and ultimately learning. We read into Atlas our desires for beauty and spectacle, our need for connection to something larger than ourselves, our hope for moments of transcendence in difficult times. This multi-layered reading is not unique to ATLAS, but characterizes all human engagement with the cosmos. When we look at the stars, we see not just fusion reactors, but suns of other worlds, sources of light in the darkness, symbols of constancy or change. When we observe planets, we see not just rocks and gas, but potential homes for life, markers of time, wanderers, like ourselves. And when we watch comets, we see not just ice sublimating, but visitors from the deep past, messengers from the edge, reminders of our cosmic heritage. The dissolution of Atlas can be read as tragedy or as transformation, as failure or as fulfillment of cosmic purpose. The comet didn't fail, it completed its journey, transformed from solid to gas, from concentrated to dispersed, from potential to actualized. Its dissolution was not an ending but a change of state, a redistribution of matter and energy. From the universe's perspective, if it had one, nothing was lost. The atoms that made up ATLAS still exist, just in a different configuration. This perspective offers comfort but also challenge. It reminds us that our human-centered view of events is just one possible interpretation. What seems like destruction to us might be creation from another viewpoint. What appears as loss might be transformation. Atlas's dissolution dispersed organic molecules and dust throughout the inner solar system, potentially seeding future chemical reactions, possibly contributing to the ongoing chemical evolution of planets. Its death might enable future life. Yet even as we acknowledge these alternative perspectives, we cannot escape our human viewpoint. We are embodied beings with limited lifespans, and we experience the universe through the lens of our mortality. When we see a comet dissolve, we cannot help but see an echo of our own impermanence. Atlas became a memento mori, a reminder that all things pass, that even objects that have existed for billions of years can disappear in a matter of weeks. This recognition of impermanence might seem melancholic, but it can also be profoundly meaningful. The fleeting nature of Atlas made its appearance precious. Had it been a permanent fixture in our sky, we might have taken it for granted. But knowing it would pass, that we had only a brief window to observe it, made every observation valuable. The comet's transience heightened our attention, intensified our appreciation, made us more present to the cosmic moment. As we reflect on Atlas and its meaning, we are drawn to consider the nature of the message it carried. Every comet is a messenger, carrying information from the distant past and the distant reaches of the solar system. But what exactly was Atlas trying to tell us? If we could decode its message fully, what would we learn? The answer lies not in any conscious intent on the comet's part, but in the information encoded in its composition, structure, and behavior. The chemical message of ATLAS was written in molecules. Every spectral line told us about the conditions in which those molecules formed. The presence of hypervolatiles like carbon monoxide told us about formation temperatures below 30 Kelvin. The isotope ratios told us about chemical processes in the early solar nebula. The organic molecules told us about the prebiotic chemistry that preceded life. Atlas was a library of chemical information, each molecule a word in a story written over billions of years. The physical message was written in the comet's structure and behavior. Its fragility told us about the gentle accretion processes in the outer solar system. Its fragmentation pattern told us about the distribution of volatiles within the nucleus. Its rotation and outgassing told us about the complex dynamics of sublimating ice. Every aspect of Atlas's physical evolution was informative, teaching us about processes we cannot directly observe or replicate in laboratories. The orbital message connected Atlas to the larger architecture of the solar system. Its path told us about gravitational perturbations in the Oort cloud. Its connection to the 1844 comet told us about cometary families and fragmentation cascades. Its hyperbolic trajectory told us it was making its first and only visit to the inner solar system. The comet's orbit was a thread connecting the visible to the invisible, the known to the unknown, the present to the deep past. But perhaps the most profound message of Atlas was not written in molecules or orbits, but in its very existence and dissolution. The comet reminded us that the solar system is not a static stage, but a dynamic, evolving system. Material is constantly in motion, being transformed, recycled, redistributed. Atlas showed us this process in action, compressed into a human timescale. We watched billions of years of preserved history dissolve in weeks, saw ancient ice turn to gas, witnessed the transformation of order into entropy. This message of constant change and transformation extends beyond the physical to the philosophical. Atlas reminded us that our knowledge is always provisional, subject to revision. What we think we know today might be overturned tomorrow by new observations. The comet we thought would be spectacular became a lesson in fragility. The object we thought was robust proved to be delicate. Our certainties dissolved along with the comet's nucleus. Yet this uncertainty is not a weakness, but a strength of the scientific method. Science progresses through failed predictions, through surprises, through the constant testing of ideas against reality. Atlas contributed to this progress, adding its data to our ever-growing understanding of comets and the solar system. Every failed prediction is a successful experiment if we learn from it, and we learned much from Atlas. The message of Atlas also speaks to resilience and adaptation. The comet couldn't survive its encounter with the Sun, but its material continues in new forms. The dust becomes part of the zodiacal cloud. The gas joins the solar wind. The organic molecules continue their chemical evolution. What seems like destruction is actually transformation. What appears as ending is really continuation in a different form. This is a profound lesson for beings like us who fear endings and cling to permanence. As we near the end of our contemplation of ATLAS, we must consider what it means for future comet observations. How will the experience of ATLAS change how we approach the next bright comet? Will we be more cautious in our predictions, more prepared for disappointment, or will we maintain our capacity for hope and excitement, knowing that even failed expectations can lead to wonder and learning? The answer probably lies somewhere in between, a balance of hope and realism, excitement and caution. The next dynamically new comet discovered will inevitably be compared to ATLAS. Astronomers will watch for signs of fragmentation, for evidence of hypervolatile content, for indications of structural fragility. The lessons learned from ATLAS will be applied, our models refined, our predictions perhaps more accurate. But the universe will undoubtedly still find ways to surprise us. Each comet is unique, and the next one might behave in ways we haven't anticipated. This ongoing dance between prediction and surprise, expectation and reality, is part of what makes astronomy so engaging. We are constantly refining our understanding, getting closer to truth, but never quite reaching certainty. The cosmos keeps us humble, reminds us that there's always more to learn, always another mystery to explore. Atlas was just one note in this ongoing symphony of discovery, but it was a particularly poignant one. The public engagement with Atlas also offers lessons for science communication. The excitement generated by early predictions brought many people to astronomy, who might not otherwise have paid attention. Even though the comet didn't deliver the promised spectacle, the journey of following it, learning about comets, understanding why it fragmented was valuable in itself. The challenge for science communicators is to maintain public interest even when cosmic events don't unfold as dramatically as hoped. This points to a deeper truth about human engagement with the cosmos. We are drawn not just to spectacle but to story, not just to events but to meaning. Atlas became compelling not because it was bright, but because it had a narrative: discovery, promise, transformation, dissolution. This narrative engaged people emotionally as well as intellectually. It made the comet more than just a celestial object. It made it a character in a cosmic drama. As we look to the future, we can be certain that other comets will come. Some will be spectacular, fulfilling our hopes for celestial grandeur. Others will be like Atlas, offering different lessons, subtler beauties. Each will add to our understanding, our experience, our connection to the cosmos. The key is to remain open to whatever each comet offers, to find value not just in spectacle, but in science, not just in fulfillment, but in surprise. The technology for observing comets continues to advance. New surveys are coming online that will detect fainter objects farther from the Sun. Space telescopes with unprecedented resolution will reveal details we can't currently imagine. Spectroscopic techniques will identify molecules we've never detected in comets before. Each advancement will allow us to read the messages comets carry more clearly, to understand their stories more completely. But technology alone isn't enough. We also need the human element, the curiosity to look, the patience to observe, the wisdom to interpret, the humility to be surprised. Atlas reminded us that all the technology in the world can't eliminate uncertainty, can't guarantee predictions, can't remove the element of mystery from cosmic events, and perhaps that's as it should be. A universe without surprises would be a universe without wonder. As our contemplation of Atlas draws toward a close, we return to the fundamental question: did we misread it from the beginning? The answer we now see is both yes and no. Yes, we misread its brightening as a sign of future spectacle, rather than impending dissolution. But no, we didn't misread its significance, its value as a teacher, its role as a messenger from the deep past. We read it as humans must read the cosmos, through the lens of our hopes and limitations, our knowledge and ignorance, our desire for meaning and our confrontation with meaninglessness. The story of Atlas is ultimately a human story projected onto a cosmic event. It's a story of expectation and surprise, hope and disappointment, prediction and learning. It's a story that reveals as much about us as about the comet. In watching Atlas, we see ourselves reflected, fragile beings in a vast universe, trying to understand our place, seeking beauty and meaning, learning to accept both spectacle and dissolution as part of the cosmic dance. The dust of ATLAS continues to spread through the solar system. Some of it will reach Earth, becoming shooting stars in our atmosphere. When we see these meteors, we might remember the comet that didn't quite live up to our expectations but exceeded them in unexpected ways. We might remember the lesson it taught about fragility and transformation, about the danger of certainty and the value of surprise. We might remember that we witnessed something rare and precious, the dissolution of a 4 billion-year-old object, the transformation of ancient ice into contemporary gas and dust. In the end, Atlas gave us exactly what we needed, though not what we wanted. It gave us a lesson in cosmic humility, a reminder of the universe's capacity for surprise, an opportunity to refine our understanding. It gave us a shared experience, a collective focus, a common story. It gave us data that will be analysed for years and memories that will last a lifetime. It gave us a moment of connection to the deep past and the vast cosmos. And perhaps most importantly, it gave us a reminder that we are part of something immense and ancient and ongoing, something that includes both spectacular comets and dissolving ones, both fulfilled expectations and confounded ones, both answers and endless questions. The night continues to turn above us, filled with stars and planets, asteroids and comets. Somewhere out there, another chunk of ice is falling toward the sun, carrying its own message, its own story, its own potential for surprise. We'll watch it with instruments and eyes, with hope and caution, with scientific rigor and human emotion. We'll probably misread it in some ways, project our expectations onto it, see what we want to see. But we'll also learn from it, be surprised by it, add its story to our ever-growing understanding of the cosmos. Atlas has become part of that understanding, a chapter in the great book of astronomical knowledge. Its story is now our story, its dissolution part of our experience, its lessons part of our wisdom. We watched a comet die and learned something about how comets live. We saw ancient ice sublime and understood something about preservation and transformation. We witnessed a cosmic event that disappointed our expectations and discovered that disappointment itself can be a teacher. The message of Atlas, if we can distill it to its essence, might be this. The universe is not obligated to meet our expectations, but it always exceeds our imagination. What we think we want from cosmic events, spectacular shows and dramatic displays, might not be what we most need. Sometimes the quiet dissolutions teach us more than the bright spectacles. Sometimes the failed predictions advance our understanding more than the successful ones. Sometimes the comets that disappoint our hopes fulfill a deeper purpose, reminding us that we are students of a cosmos that still has much to teach us. As we prepare to leave Atlas behind and return to our earthly concerns, we carry with us the memory of a comet that came and went, promised and dissolved, brightened and faded. We carry the knowledge gained from its observation, the data collected from its dissolution, the lessons learned from our misreading. We carry the humility of beings who thought they knew what would happen and were proven wrong. And we carry the wonder of conscious creatures capable of observing, interpreting, and finding meaning in the dance of ice and light that plays out in the darkness above us. The story of Atlas is complete, but the story of our engagement with the cosmos continues. Other comets will come, other surprises await, other lessons will be learned. We'll keep watching, keep wondering, keep misreading and reinterpreting. Because that's what we do. We are the universe's way of observing itself, understanding itself, finding meaning in itself. And every comet, whether spectacular or disappointing, whether robust or fragile, whether fulfilling or confounding our expectations, is part of that ongoing process of cosmic self-discovery. Atlas has returned to the darkness from which it came, but transformed. It is no longer a solid body, but a dispersed cloud of atoms and molecules, dust and gas. These particles continue their journey through the solar system, carrying with them the story of a comet that was, for a brief moment, the focus of human attention and hope. Some of these particles will find their way to Earth, becoming part of our world, part of us. In this way, Atlas achieves a different kind of immortality, not as a spectacular comet, but as a contribution to the ongoing chemical evolution of the solar system. We too are transformed by our encounter with Atlas. We are not the same observers who first spotted that faint smudge of light in December 2019. We have learned about cometary fragility, about the complexity of these ancient objects, about the difficulty of prediction and the value of surprise. We have experienced hope and disappointment, excitement and acceptance. We have participated in a cosmic event that connected us to the deep past and the vast scales of space. We have been reminded of our place in the universe, small but conscious, limited but curious, mortal but capable of touching eternity through our observations and understanding. The final message of Atlas might be this. We are all temporary arrangements of matter and energy, briefly organized into patterns that can observe and appreciate the cosmos. Like Atlas, we are fragile. Like Atlas, we are ancient, made of atoms forged in stars billions of years ago. Like Atlas, we are on a journey through space and time, and like Atlas, we will eventually dissolve, our atoms returning to the cosmic cycles from which they came. But before that dissolution, we have this moment, this capacity to witness and wonder, to observe comets and find meaning in their stories. That capacity, fleeting though it may be, is perhaps the most remarkable phenomenon in the universe. Matter organized in such a way that it can contemplate itself, find beauty in its own transformations, and share that beauty with others. A TLAS reminded us of all this and more. It was a teacher disguised as a disappointment, a profound lesson wrapped in a failed prediction. It showed us that the universe's gifts don't always come in the packages we expect, that sometimes the most valuable experiences are the ones that confound our expectations. It taught us that dissolution can be as beautiful as spectacle, that scientific failure can be as valuable as success, that cosmic events don't need to meet our hopes to exceed our imagination.